Welcome back. We're now going to do the second of our consolidation worksheets. This is worksheet 4B3, and it is the second set of consolidation problems on special relativity. So let's look at question 1. A cosmic particle has a rest mass of 1.4 by 10 to the minus 26 kilograms there. And when it is moving at 0.99 C, the particles are observed to take 3.2 microseconds to decay. So we're going to find out its length of time that it will take to decay if it is stationary. We're going to find the kinetic energy of the particle as it's moving at this relativistic speed here. We're going to work out the rest energy of this particle, and we're going to find the momentum of the particle when it's moving over here. Okay, so let's start. So let's just write down all of the information that we know. The rest mass, which is m0, is equal to 1.4 by 10 to the minus 26 kilograms. The velocity that it's traveling at is 0.99 c. And it's observed to take a decay at 3.2 microseconds. Okay, so A is asking us to work out what would be the decay if it is not moving, in other words, in a rest frame, if it was stationary. So this value here would be a longer value than we would normally see for this particle. So, as for all of these special relativity cases, we need to find that gamma factor. So gamma is 1 over the square root of 1 minus 0.99 squared. Let's do that one. 1 over the square root of 1 minus 0.99 squared. That's 7.0888, and so on. This is a time dilation question, so TV would equal gamma T naught. Now, 3.2, that number there is the larger number. That's what we observe. We're observing a decay value which is longer than it should be. If this particle was stationary, it would decay in a much quicker time. So this must be TV, okay? So that's 3.2 microseconds equals 7.0888 T naught. So working out with T naught would be 3.2 divided by that number. So it's 3.2 divided by that number. So it's 0.45 microseconds. Okay. Right, that's A. Now B is asking us to now find the kinetic energy of the particle. So we've memorized, hopefully now, that the kinetic energy of a relativistic particle is equal to m naught c squared gamma minus 1. Okay, it's easier to just remember this formula and just simply apply it. The other option is you could do it from first principles and say the kinetic energy is I'll just write that up properly. Gamma m naught c squared. So that's the increased mass times c squared. That's the energy equivalent of the particle traveling at 0.99 minus its original value of m naught c squared. This is the rest energy there. Okay. Obviously, this one over here is just the factored version of that. Okay, so this is the total energy of the particle traveling at relativistic speed minus the actual energy at rest. The difference between this would have to be the kinetic energy. Right, so we're just going to use this formula over here. So I need the rest mass, and I've given that. That's 1.4 by 10 to the minus 26. Then we're going to multiply by c squared. I'm just going to write that. And the gamma is 7 point that. So we're going to be using 6 point that. Okay. And putting that into our calculator, it's 1.4 exponent negative 26 times 3 exponent 8 squared times, now it's going to be 6.0888, okay, and then that's the value there, which is 7.67 by 10 to the minus 9 joules, also known as 7.67 nanojoules. Okay. The third thing we need to do is find the rest energy of this particle. Now, the rest energy would be this value over here. Okay. Remember, this is the energy here of the particle, including its rest energy and the kinetic energy. Okay, so this first term here is the rest energy and the kinetic energy combined. This is just the rest energy. So the difference between this is the kinetic energy. That's how we work that out. So I'm just going to use this one over here. So the rest energy, as you know, is given by the famous equation E equals mc squared, but m naught c squared. This is the rest mass, which is 1.4 by 10 to the minus 26 times c squared. So 1.4 exponent negative 26 times 3 exponent 8 squared gives us the rest energy of 1.26 by 10 to the minus 9 joules, also known as 126 nanojoules. So this is the rest energy. This is the energy. If I was to take that entire cosmic particle and annihilate its value into pure energy, this would be the energy equivalent. So that's that value up here. This value here was that value. So the difference between it would be this value here, which is the combined energy of the particle traveling at the velocity that is 0.9 c. Right, the last thing we're asked to do here is find the momentum of the particle. So the momentum of the particle, d, is given, so the momentum of the particle velocity is gamma mv. I like using that formula rather than mv equals gamma rho naught, because that refers to the Newtonian physics. Okay, so this is 7.0888 times by the mass, and that is 1.4 by 10 to the minus 26 times by the velocity, which is 0.99 times 3 by 10 to the 8th. Don't forget, it's not just multiplied by that number there, that's 0.99 c. So putting that in, 7.0888 times 1.4 exponent negative 26 times 0.99 times 3 exponent 8. And the momentum of this particle is, so I'm just trying to find it, 2.94 by 10 to the negative 17 Newton seconds. Okay, let's do question 2 now. Question 2 says a stationary particle has a rest mass of 2.56 by 10 to the minus 22 kilograms, and it decays in 4.2 milliseconds. It's observed, sorry, I was just reading the question. The stationary particle has a rest mass of that, and it decays in 4.2 milliseconds, but is observed to decay in 6.3 milliseconds. So it's observing that it's decaying at a longer time, because this means that this particle must be in motion. So what we're going to do is find the kinetic energy of this particle and the observed mass of the particle as it moves. That's the relativistic mass, that concept that of that the slope of the graph getting larger. Rightio. So let's start with the kinetic energy. Okay. To find the kinetic energy, we need to find the gamma factor. So let's have a look at what we need to find the kinetic energy. So let's just write down the formula. So 2a the kinetic energy is equal to mc naught gamma minus 1. So I know the mass it's given to us as, oops, I'm talking about C naught on the wrong one. So let's rewrite that. So distracted. M naught C squared is what I meant to write there. A gamma minus 1, where M naught is the rest mass, obviously the speed of light, gamma minus 1. So is there a way of getting gamma here? Well, this is a time dilation problem, so TV would equal gamma T naught, and the two decay times are 4.2 milliseconds and 6.3 milliseconds. The longer one must be the dilated time, so that must be TV, and the shorter one here would be the time that it would be if it was stationary, which is said that is what the value is in the question. So putting that value in, we get 6.3 milliseconds is equal to gamma 4.2 milliseconds. Now the milliseconds on both sides cancel, and therefore gamma would equal 6.3 on 4.2. So 6.3 divided by 4.2 is 1.5. So now we have a gamma factor, so I can find the kinetic energy. So the kinetic energy is equal to the rest mass, which is 2.56 by 10 to the minus 22, C squared, and then it's gamma minus 1. Now, gamma is equal to 1.5, so it's going to be 0.5 as gamma minus 1. Putting those values together, 2.56 exponent negative 22 times c squared, which is 3 exponent 8 all squared, times 0.5 is equal to, put that there, 11.52 by 10 to the minus 6 joules, also known as 11.52 microjoules. Okay, so that's part A. The observed mass now for B. The observed mass is going to be, let's B now. The mass at velocity would equal gamma times its original mass. Okay, so this is like the time dilation formula. All it's saying here is as we go faster, the observed measured mass appears to have more mass in it by it's a multiplying of the gamma factor by its rest mass. We already know what the gamma factor is, it's 1.5 times the rest mass, which is 2.56 by 10 to the minus 22. So that's 2.56 exponent negative 22 times 1.5. So it appears to be that many kilograms, which is 3.84 by 10 to the minus 22 kilograms. And this is because the mass of the total mass of an object is equal to the mass of its components, it's also known as its rest mass, plus E on C squared. This amount over here adds to the total mass. So this part over here is making well, that's not equal to it, but this part here is increasing it up to this value here. Okay, and when you add these two together, you get that value there. So this plus that equals that. Okay, rightio. So that's questions 1 and 2. I will do questions 3 onward on the next video.